Have you ever stopped to wonder what gives a material its properties? From the stickiest feet in the entire animal kingdom to the tech that literally cleans the air we breathe, the answer, it turns out, is hidden deep inside, in the world of atoms. We're about to dive into that world, and what we're going to find is that both perfection and, believe it or not, imperfection are the keys to engineering our future.
Okay, let's start with the Gecko. This little guy pulls off what looks like a magic trick every single day. I mean, it can scamper up walls, hang upside down from the ceiling, and get this, it's so strong it can support its entire body weight on just one toe. It is an absolutely astonishing feat of natural engineering.
So the big question is, how? How does it do it? Is it some kind of weird suction cup, a biological superglue? Well, the real answer is so much more fascinating, and it's going to take us right down to the atomic level.
All right, let's peel back the layers on the Gecko's sticky secret. This is a masterclass in physics that scientists, even today, are still learning from. So, all the obvious ideas? Yeah, they're wrong. It's not glue, and it's not suction. The Gecko's grip really just comes down to a massive numbers game. You see, its toe pads are covered in millions, literally millions, of microscopic hairs. Now, each one of those hairs exerts a tiny, almost unmeasurable little pull. But when you add all of them up, you get an incredibly powerful bond. That tiny force, when you multiply it millions of times over, has a name. It's called a van der Waals force. It's this weak little attraction that happens anytime molecules get really, really close. The Gecko's whole trick is that it has enough of these tiny hairs to get enough molecules close enough to a surface to make these weak forces unbelievably strong together. Okay, so let's zoom out from the Gecko's foot for a second and look at the fundamental ideas that control pretty much all solid materials. We're about to see how this same way of thinking at the atomic level applies to, well, everything around us. At the very heart of materials science, there's a simple, elegant rule. Whether a material is super hard like a diamond or soft like the graphite in your pencil, it all comes down to how its atoms are arranged and how they bond with each other. It's like this invisible atomic dance.
Now, our understanding of that dance has changed over time. We started with what's called the Bohr model, that simple picture of electrons orbiting a nucleus like tiny little planets. But now we know it's a lot more complicated and a lot weirder. With the wave mechanical model, an electron's position isn't some fixed path. It's more like a probability cloud. And getting this more accurate view is absolutely essential for understanding how atoms really interact.
And this gets to one of the most important rules in all of quantum mechanics. An electron's energy isn't like a smooth ramp where it can be at any level. Nope, it's more like a staircase. Electrons can only exist on very specific energy steps, or quantized levels. This rule is what dictates exactly how atoms can, and, just as importantly, cannot, bond together.
So knowing this, you might think that the strongest, best materials must be the most perfect ones, right? With every single atom lined up in flawless, beautiful order. But let's explore that idea for a second, what I like to call the myth of the perfect material. In theory, on paper, this is what a perfect material would look like. It's a perfect, repeating three-dimensional pattern of atoms. We call it a crystal lattice. It's this beautiful, ordered structure that materials scientists use as their ideal baseline. But what does a real material look like? Well, this is a cross-section of a copper ingot. And you can see right away it's not one single perfect crystal, not at all. It's actually made up of tons of smaller crystals called grains, all jumbled together and pointing in different directions. Already, our idea of perfection is kind of falling apart.
Because here's the reality. A truly perfect solid just doesn't exist. Every material, no matter how pure it is or how carefully it was made, is absolutely full of defects. These atomic scale flaws are everywhere. And this isn't some minor detail. It's fundamental to how materials actually work in the real world.
So, if nothing's perfect, is that a bad thing? Well, far from it. As we're about to see, these so-called imperfections are often the very source of a material's most useful and powerful properties.
Let's look at a modern marvel of engineering you probably use every single day, the catalytic converter in your car's exhaust system. Its whole job is to take the harmful pollutants coming from the engine and turn them into much safer gases before they ever reach the air.
And how does it work, this chemical magic? Not with a perfect, pristine crystal. No way. The incredible efficiency of this device comes from precisely engineered defects on the surface of its special materials. The flaws are the feature.
If we could zoom in with a ridiculously powerful electron microscope, we could actually see the surface of these tiny catalyst crystals. We're talking about a scale of just a few nanometers here. And you can see the surface isn't perfectly flat. It's covered in these atomic scale steps and ledges.
And here's what's so cool about that. These surface defects, the ledges, the kinks, even a single atom that's just sitting on top, they're special. They are high-energy sites that are really chemically reactive. So pollutant molecules are naturally drawn to these exact spots, where they can latch on, break apart, and then recombine into safer molecules. The imperfections are literally the reaction hotspots.
So to be a little more precise, a crystalline defect is really just any irregularity in that repeating pattern of the crystal. It could be a point defect, like a single atom that's missing, we call that a vacancy, or it could be a linear defect, which is a whole row of atoms that's out of whack. We call that a dislocation. These are the basic building blocks of imperfection.
Okay, so we've seen the power of atomic bonds with our Gecko, and we've seen the power of atomic defects with the Catalyst. Now let's see how this all comes together in the modern science of engineering brand new materials.
This really brings us to the core of modern material science. It's all about mastering both sides of the coin. First, you have to understand the fundamental forces that hold atoms together, like those van der Waals forces the Gecko uses. And second, you have to understand the nature and the effect of all those atomic defects. Once you combine that knowledge, you can start to create materials with properties we've never seen before.
And we can bring this whole thing full circle, right back to our Gecko. By truly understanding the Gecko's secret, scientists have actually engineered a new kind of surgical adhesive. It's a biodegradable tape that can close wounds without any staples or stitches, and it even works in wet environments, like inside the human body. It's a perfect example of learning from nature's mastery of atomic forces.
This quote it captures the essence of this whole story perfectly. Material properties are incredibly sensitive to flaws. But as we've learned, flaw isn't always a bad word. In the world of materials, imperfections can be powerful tools.
And all this leaves us with a pretty fascinating question for the future, doesn't it? We are finally learning how to control matter at the atomic level, embracing and even engineering its flaws on purpose. So from self-healing metals to ultra-efficient catalysts, what seems impossible today might just be the next perfectly imperfect material of tomorrow.